Hey, and welcome to this recording on security testing. My name is Christoph Ebert. I'm the Managing Director of Vexor Consulting Services, and I will guide you through this recording, through this recorded webinar, and will introduce you to security testing methods. The topic as such will be structured in a brief intro into the challenges, some terminology and standards. Then we dive into some testing methods, verification, validation, and also summary and discussion in order to finalize. Now let us move into the brief introduction, who we are, what we are doing. Vector is a company with worldwide coverage, about 3,500 engineers working globally, about 1 billion sales in 22. And we have different product lines with PLM, ALM, with embedded software, where we are market leader, for instance, with AutoSAR. Testing, that was our start. And we are still a leading tool provider for test solution, which of course also fosters our interest in testing for cybersecurity. We work on diagnostics, on calibration, and we have services, which is my responsibility. The topics are quite broad. Let me just focus on the scope of what we call trust in our consulting activities, which is that we, on the one hand side, introduce standards, because there is a wealth of standards which all relate to each other. And with these many standards, it's good to have experienced consultants who know how to do that efficiently and still passing the audits. But we also work hands-on, doing TARA, doing pen test. We have a global pen test lab in different places, such as Germany and Korea and China. And we also perform supplier audits. We help in building up the test methodology, both in terms of security and safety, and also the combination of both, which is, for instance, necessary if you have high criticality systems such as braking, steering with ASIL C or D. But we do that, of course, also on the level of QM. We perform trainings, we help in technology evolution, such as architecture evaluation, and we perform also agile transformations. Short word on myself. As said, I'm responsible in Vector for the consulting activities. Aside that, I'm also authoring books. That's a kind of a hobby activity. I'm also doing lots of music, especially pipe organ is recently my favorite. And I teach the engineers of tomorrow here in Stuttgart, Germany, and also in Paris at Sorbonne University, in order to grow the competencies of the future engineers. Let us look in the challenges of cybersecurity. And I want to start with a very important topic, which is product liability. The legal exposure is growing across industries. And we see here industrial IoT, which is a kind of a complete picture of what we can really perceive in terms of attacks. And what we see is the amount of system being attacks. And there was a steep increase in 2020, which is clear because that was the pandemic situation with a lot of unprotected, let's say, home office situation. This has, again, let's say, bit mitigated in 21, 22. But nonetheless, we see in total an increase. And we see at the same time, you see that on the right side in this presentation, that many companies have no established product cybersecurity program. We see over 80% of all code is more than 4 years out of date, and half of the code have high vulnerabilities when we pass on static analysis. So cybersecurity is clearly the call of the day. And zooming into automotive, and this is from a recent database where we look into end of 21, all reported cybersecurity attacks on OEM and Tier 1, we see an almost exponential increase with a focus on premium cars, with a focus on autonomous and automatic cars. And we see the top 5 attack points are a bit similar as we have seen them also 1 or 2 years ago. Is the key fob, is server attacks, smartphone, OBD, head unit, but increasingly the back office, because we have this convergence of the product IT and the enterprise IT. In other words, we have a convergence of EE and the business IT, which is used to feed our IT in the cars with software updates, with services, etc. We see also that a majority of the attacks is done by black hat hackers, and the other half by a little bit less than half by white hat. That is, some do it to prove that things are possible, some do it in order to abuse the situation. Most is in the meantime done remotely. And that means if we look to all cybercrime today, it's more profitable than the global illegal drug trade. Now, for the illegal drug trade, as well as for any other criminal activities, which include cybersecurity attacks, there are no precise figures. We do not know how much companies pay in terms of getting rid of ransomware. But generally speaking, the estimates of those who should know is that we in the meantime exceeded with cybercrime. And that's further growing. There are entire countries who finance their own budget by cybercrime activities. And this has increased now in a situation where we see the critical dimension of cybercrime in times of war, because there we also perceive that we are now in a situation where some countries attack the world, the companies, with cyber attacks just as a kind of a revenge in terms of whatsoever would be motivation. In other words, the situation is getting worse by the day. Now, looking into automotive, which is our focus here, we have this evolution, which we call ACES, Autonomy, Convergence, Ecology, and Services, which brings a lot of new vulnerabilities into the picture. And that means, since a majority of the attacks is detected by a third party, will also be exploited. That's what we know from IT systems. That's my own past. I grew up in IT. I grew up in security activities since my study in US, where I was basically directly related to doing some cure in some cyber attacks. Until today, we have seen a steep increase, and we at the same time also a strong need to learn about how do we effectively verify and validate. Before that, let's look into the standards, because standards build the basis of what we call the state of the practice, the state of the art, which again is what is demanded in terms of being safe with respect to the standards, and that means with respect to product liability. The legal situation is what we see here in 3 paths. We have functional safety, we have cybersecurity, we have homologation. Functional safety, the basis, which is governed by standards like ISO 26262 in the automotive world. And there are many other related standards in other industries. We do have an increasing new application domain, which is related to AI, learning and flexible systems, for instance, covered by the safety of the intended specification and solution. And that means that we have increasingly amount of standards which impact safety. We then have the cybersecurity, the 21434, and also existing IoT and IT cybersecurity standards. We have TISAX. And for the homologation, we have the UNECE, RX regulations, the 155, which is cybersecurity management system, and the R156, which is software update management. Those directly play into what is cybersecurity. We need safety because there is no safety without cybersecurity. We need homologation because this is the way how vehicles are brought into the usage. And we have underlying models, which you see on the bottom, which is on the process maturity, the ISO 33000 series, but also the classic product development with ISO 9001. Let's look a little bit closer to the 21434. We see similarities to the 26262. Both are risk-oriented standards. Both cover culture, that is not just giving engineering guidelines, but also clearly distinguishing the organization level, the project level, and the activities related to cybersecurity implementation, operation until end of life. And that means we do have here a standard which helps in implementing, but it's not a guidebook, it's not a methodology, it's open to methodologies. And that's a frequent misunderstanding in the whole picture, that some companies, some people think that if we have the 21434, we can apply a copy-paste exercise and we get a framework how we should structure our organization. This is not the intention of an ISO standard. The ISO standard gives goals, it gives expectations, it gives requirements, but you have to implement and you have to tailor your process and method according to the needs of your business, to your product, and of course also to these standard requirements. And from that perspective, we consider 21434 much more useful than the 26262, which is extremely detailed in prescribing almost anything and therefore making it very difficult to even understand what applies, because the 26262 is also far from perfect. I mean, as an expert, we find continuously gaps in this standard. And that's exactly the risk if you try to be prescriptive, like the authors of 26262 try, you will never come to an end. If you try to be explanatory, like 21434, then you achieve your goal because it's more a level of understanding, culture, and education. Therefore, 21434 certainly is a better baseline than a heavy book, which will never be perfect and which you have in effect continuously update. Of course, we don't do that with an ISO standard. So that means the 26262 is in a way technically outdated before even used. And that is a situation which is a pity for ISO standards. But okay, let's look forward. We hope that the 21434 stays sober and therefore also useful. Let's now look into testing. In testing, we distinguish two major methods: verification, validation. Verification is what we do in terms of the right process in order to deliver a product, a component, a deliverable, a work product, which follows the needs of cybersecurity. That is, we call it also doing things right. That's what I always tell my students. It's pretty simple. Verification is about doing things right. That is process. Validation, on the other side, is doing the right things. So we take an external perspective. We have to do the right things in order to really release the product. The right thing means the right security level. And that means we have to do things right, process, and we have to ensure that the work products are in line with expectations. And this is the validation. So this is how these two activities relate to each other. We typically distinguish the verification more in terms of how we specify, how we implement, how we do, for instance, a code static analysis, a unit test, that are typical verification activities, while on the side of validation, we look more towards what are the interfaces. Penetration test is a classic activity for validation. Fuzzing would be a validation activity. And of course, anything related to interface tests, system tests. Of course, also the whole homologation would have more aspect also with respect to validation. So very clear homologation as requested by the R155, that is Cybersecurity Management System, looks very much also into how are you doing things. So it's also about verification. Now, generally speaking, we have to systematically follow the standards, but we should not engage into a copy-paste exercise of our standards. And that brings me to a very important statement, which is what we call security by life cycle. there's not the one activity in cybersecurity validation or verification which yields a huge amount of defects. They all build upon each other. This is like regular testing. Those of you who have a test career, like myself, I've been in testing and requirements engineering for almost a strong part of my professional career. What we know is that all these different activities not only build upon each other, but they also have their specific focus areas. Some help in detecting specific vulnerabilities. Others help in preventing the occurrence of the vulnerability, like, for instance, making some memory robustness checks, making some checks with respect to inputs, avoiding or preventing buffer overflows. These are all design activities which support cybersecurity. Further upwards in this V model, where we go to the higher level of abstraction, where we also see the more systemic perspective, we look into how can we sabotage, how can we attack the system, and we will then also look into activities such as update management over the air or via OBD. We look into the classic key fob attack, the man in the middle, and that is, we will have a variety of activities which we engage. And what we see here is in this overview is different activities, code and design analysis, that's on the bottom of the V. And we have fuzz testing, which we can do on unit, on component, and on system level, where we push to the interfaces random or pseudo-random data, which kind of generates, for instance, load situations, which generates boundary situations, but randomly. We can do that also more focus with specific crackers, vulnerability scanners. That are things which we also use our vector tools, like the Canui tool, in order to really push specific messages to the interfaces. Then we have the pen testing where we connect the negative requirements such as misuse, abuse, and confuse cases with the functional requirements. We have developed here a specific gray box, a test method, which I will explain in the later part of this recording. And we also have very specific activities like denial of service, replay, and also, again, some sort of evolutionary mechanisms like mutant-generated messages. And finally, we have the life cycle, the continuous maintenance activity, where we have on the one side the security incident response team. We have on the other side also the release of updates. And bringing back my own experiences in IT, we need to be clear that most vulnerabilities come from working under pressure. In other words, if you release the product, make late changes, the chances are high that you introduce severe vulnerabilities. And we have seen that with the Heartbleed, which was some years ago. That was a change which was done by a person. For time reasons, there was no reviewer, so a single person made a change. The change was released, and that was one of the biggest IoT bugs which ever went into the real life. And Heartbleed was a very expensive repair activity, but essentially happening because there was no peer review of the changes which had been done by a single person. I'm not going to blame that person. What I say is we need a process. And it brings us back to verification, doing things right. This is the major message here when we talk about security by life cycle. It's not simply brute force testing. That's what some people think would be the necessity of test. Test is much more than brute force. Test is a methodology, is a set of methodologies, starting from unit tests, where we find a lot of different methods which enrich each other, coverage schemes, C0, C1, MCDC, but also the clear targeted specification of unit test data, like we do with our vector cast environment. where we generate test cases for specific vulnerabilities. These are the topics which are really relevant. So let us look into the topic of what is here the traceability need, because this is really a very big support in the enhancement of cybersecurity. In other words, we look to the requirements where we specify functional and quality. I mentioned already we have positive and negative requirement. So the naive, let's say, requirements engineer, the beginner, they typically focus on functional requirement. The experts know that there is a lot of other type of requirement, constraints, quality requirements. What we focus very much on cybersecurity is on negative requirements, requirements which we use in order to specify situations which must not happen. And this gets in the meantime more and more relevant because we have similar situations also in evolutionary systems such as AI-driven autonomous systems, where we need to make sure that the safety, and that is always why we do all this, of the intended functionality is specified correctly. That means we also have to think in terms of what would be exception cases, what would be potential error cases, and what is actually the intended functionality. Too often, requirements like designers think in terms of the sunny day scenario. And this is past, this is ancient thinking. Today, we have to think about, let's say, the rainy, the stormy days. Cybersecurity is about the bad and the ugly. And we have to think, as I always say, we have to think like a criminal and act like an engineer in order to specify our testing. And therefore, we need these different test activities, and we need also a clear traceability in order, for instance, to show that we really did our job during testing. And that is, again, necessary to mitigate liability risks. So let's look into some of the tools which we are using. This is now an example from our VectorCast environment, where you see different type of KPI. You see visibility on which component have been covered, what kind of, what type of vulnerabilities have been found. We look into code errors, such as one of the very typical error, the null pointer, which is often in Linux system, a weakness, parameter passing in C language, memory management, especially where you have direct memory access. I'm aware that today with an AutoSAR, which builds upon the, let's say, classic library, which includes the crypto stack, starting with HSM upwards, would not really have these issues. But from a testing perspective, and that is what we do every day, when we receive issues or whole vehicles for pen test, we see also from many of our Tara, which we might do here and there, that not everything is built on a clean AutoSAR stack. A lot is still with real-time operating systems, with more ad hoc environments or legacy, where we need to be careful to avoid this before mentioned vulnerabilities on the level of programming. Then we have, for instance, design errors like a mismatch of what is read-only or what is a read-write. How do we declare the parameter typing? How do we ensure that there would be no mismatch? And also to make sure a clean and robust exception handling. Because unlike an IT system, we can in the car not at all do a reboot. We cannot simply make a kind of information to the driver, this is what you need to do. This is, by the way, also why we have the difficulties in our cybersecurity architectures, that if we just report incidents, this is not enough. I mean, we can do that offline to the cloud so that the OEM can start their own activities. But within the vehicle, we have to fail operational, and we have to make sure that all these different exception cases would be handled properly. And that is exactly why we also have to test these different sideways, not only the sunny day scenario. Now here an example, we parse through software code, source code on a unit level, where we can check a variety of analysis, both static and dynamic, Static means code parsing with static analysis tools, and like PCLint, which is part of our vectorcast. And at the same time, we can also run dynamic unit test cases where we see how the data flow would happen on the level of the unit. We can do that automatically, such as a Jenkins pipeline where this would run with each new update. And we get automatic KPIs, which give us an overview into the vulnerabilities of the source code. Now, if we move a little bit upwards, if you remember the V, we had on the lower level the code with verification, static dynamic. Then we move upwards, we come into the component, the interfaces, where we use interface scanning, etc., and also the network integration. Here, our standards, which is based upon the before mentioned 21434, but also to a certain degree the safety standards 26262 and the ISO PAS 21448, they all bring forward specific test methods. And this is exactly what we can see in this picture. The different stages, the different abstraction of these test methods and how they extend each other, such as, for instance, if we go where we already spoke about the static analysis, then we go into some specific testing with respect to functionality, both positive, negative. Then we, for instance, learn about topics like fault injection, which can help to identify the overall quality level. We then move forward also into testing in the loop, which is typically at the end stage done with hardware in the loop, simulation, for instance, corner cases, which need to be specifically tested. And that gives us a stage approach from the white box, which is understanding the code and the design, to the gray box, which is doing TARA based on components and architecture, but attacking the system from the outside, to the mere black box, which here would be on the highest level, going from the individual unit to the item, to the network, to the system, and of course also documenting. I give you one example how we do this risk-oriented security testing, which is, for instance, what we do in most of our fuzzing and also a pen test, penetration test. We have here summarized 10 steps, which we typically apply. The initial step is always a reconnaissance. That's the understanding of the system to test. You don't need to be the developer. We do that often from the outside because we are a test company. So we test from the outside. So reconnaissance, understanding the architecture, understanding the systems. Structural analysis to see about what are the building blocks. We do that on the level of what is public accessible information, because some of our clients want that we really behave like an attacker. Let's call it a professional attacker. And that is, we need to look from the outside and with the information available from the outside without social engineering. Then we elicit the assets in order to prioritize what would be major attack schemes. We move forwards into identifying then risk and vulnerabilities. That's a classic TARA from which you derive security goal. So some people ask, why do you repeat the TARA if you do a testing? Well, the answer is simple. We want to be efficient and effective. Understanding about vulnerabilities and assets and attack paths allows to focus the test. That brings two big advantages. In terms of efficiency, unlike randomized testing, which we do anyway with the fuzzing, we can focus on weakness. Like if we know a certain component is used in architecture, we try to attack this based on known vulnerabilities. That's efficiency, we focus. Effectiveness means that we capture a lot of vulnerabilities which you would never find if you focus too much only on, let's say, black box and automatic fuzzing. And that is exactly why we use these gray box techniques, which look into TARA and architecture and component. Now, of course, here our big benefit compared to other companies is that Vector has been in automotive EE for about 3 decades. And we know really inside out for each vehicle, how it is built, but also how we should attack a specific situation without being the engineers. It's just because we test and we have been testing for 3 decades, and we know how these networks work and what would be specific vulnerabilities if you use this and that semiconductor or this and that middleware, infotainment. Is it Linux-based? Is it Android-based? Is it some other infotainment? Here, the expertise over this long term really plays an advantage. Then on the right side, we now move really into the testing. We identify what would be the minimum viable penetration test cases. That helps us to focus resources, again, efficiency and effectiveness. Then we perform the test, we look to our measurements, the KPIs, and we then go backwards and say, now we have also to enrich the requirements. This is the real value which our customers get from us when we do the security testing, that we also help them to update, to improve their requirements, the functional security requirements, positive and negative. Finally, we do a regression testing if there are updates. And this is typically what we do in these different steps for penetration test. And it gives also a nice idea what we mean with risk-oriented test, because risk means that we look really into the vulnerabilities from a perspective of an informed engineer, but not the perspective of the designer. That's a big difference. We act really as an engineer with a background of, let's say, past vulnerabilities, past experiences, but not as a designer, because the designer, as I mentioned earlier, thinks too much about sunny day. This is why independent testing is so important. And what you see here in the blue boxes, these are now specific methods which we have developed, which we build the tools and which we then enhance in our pen testing. By the way, there's always also some literature. You see that in the italics here. So most what we do, we also publish in journals like the IEEE Software, ATZ. So you find also more information out there. Now, from a perspective of this practical application, you see here a small setup which we have been using for ECU testing, which we connect then to our test equipment for different type of security testing. 4 type is what we typically run: interface discovery, that is to understand how the interfaces are structured, what kind of technology. Often it's JTAG, and we have to see which paths are open. And we have sometimes the OBD, we have sometimes other interfaces like in the infotainment. Then we do the network discovery, where we analyze network traffic, and we take protocol analysis, communication patterns. That's the traditional strength of Vector. Then we start with the network penetration test, where we put information on the network data from load, performance, fuzzing, all these different type of data. We also generate changes in the supply voltage, temperatures, mechanical stress. All that would be used to really make a complete fuzzing. And we have then also the focus penetration test, where we look from a reverse engineering perspective into vulnerabilities which we can exploit. And that means in combination of these different methods, each of these have their own strength. And that is the dark red balls here, which is the strength of the respective method. But at the same time, we also see some would have a low effect. So this is why we want to combine these different techniques. And specifically in our gray box pen test, we focus really on the knowledge which we bring in order to provide a good insight into how can we attack the system and what would be a most efficient and effective usage. Let's look into a case study, which we have been doing a while ago, which is specifically for simple airbag ECU with related interfaces, where we do a comparison of gray box and black box pen test based on the method which I just explained. So the gray box would mean we start with the analysis of assets based on the reconnaissance, the structure, then we do the TARA, and then we run specific test scenarios that would now be the result of the TARA, where we know the attack vectors in this airbag ECU. We start typically with the first asset in such cases in ASIL-CD is always functional safety goals. So here would be, for instance, the unintended airbag deployment as a kind of a fault which we want to avoid. And then we see what could contribute to this unintended airbag deployment. That's a typical HARA approach. So this is a technique from safety, the hazard and risk analysis, which we then enhance to the TARA. And it also nicely shows that safety and security are connected very closely to each other. From here onwards, we run our test cases. Of course, we automate in order to make the regression test cases. We do the traceability in order to look on a coverage scheme. And we connect that with our TARA in order to analyze, for instance, based on the memory analysis, what would be specific weakness like key management. That was one of the issues here, where we found a root certificate and also a key in some area in the memory. But this is just an example, and we find typically more such things. JTAG, for instance, gives also a lot of such activities. And that in total allowed us to compare the black box and the gray box penetration test based on these KPI. And we found that from a perspective of efficiency, we need less test cases compared to the black box. And understanding that black box is also not something you should just run in fuzzing and random mode. You also have to put engineers there. As it's good to do this reconnaissance to understand the structure. And we also found a better effectiveness. Specific defect types can be easier found in one TARA-based and asset-based methodology compared to the mere black box methodology. And that is exactly what I wanted to show in this recording, that you learn about different techniques for verification and validation in cybersecurity. We looked into the different activities along the V, from the static and dynamic analysis of the code to the component and interface level up to the system level. System can be the ECU, can be a connection of ECUs, can be a whole assembly, or can be the full vehicle. They are illustrated in standards like the ISO 21434. But as I mentioned, not as a cookbook. The standard only gives a guidance, gives a set of requirements. And on that perspective, let me conclude now into what we learned in this webinar, in this recording, which is that systematic security test is risk-based and at the same time also combines different abstraction and methods from the code verification to the interfaces, the integration, the network, to the fuzzing on the different abstractions and the pen testing. We also looked into the typical steps for security-based testing. And just to give you an outlook, fresh from our labs, if I may say so, we now increasingly also push AI into risk-oriented security tests. And we just look into, for instance, can we better connect requirements engineering and the traceability with AI mechanisms into generating the necessary test cases? How can we identify or give guidance for the reconnaissance based on known vulnerability databases? So these are ongoing activities which are illustrated here in the blue boxes. Further on, I suggest that you look into what's going on in the discipline. We have here a set of different, let's say, guidance which is available online. We have our consulting activities, we have trainings, we have white papers. We also have our Compass tool for the TARA. We also recommend that you look into some of the external resources, not only the standard ISO 21434. What helps a lot is look into the common errors and vulnerabilities. Now, this is what we continuously recommend, that you look in vulnerability databases like the Mitre has a quite nice summary on the top 25 most dangerous software errors. We have CVE, which is a vulnerability database. We have specific CERT lessons learned. We have Evita and Heavens as methods which are used and referred to in the 21434. So there's a rich amount of such techniques. And our strong recommendation is ensure that your systems and software engineers get a minimum training for cybersecurity. We offer such trainings as e-learnings, for instance, which are then applied by companies. White papers and books, as you see here, quite a lot what is available. Here are a couple of recent examples of what we have been publishing on pen testing, on lessons learned from introducing 21434, but also introducing the UNEC R155, CSMS, and R156, some software update management system. These are our recent activities. We look into formal traceability, as I mentioned, also from perspective of AI. And we benefit, or we give the benefit to our customers that Vector is not primarily a security company, but we are primarily a software supplier, which really know how to build safe and secure software. And we give this kind of lessons learned in our many customer projects, basically working with each single OEM and tier one worldwide to the advantage of our customers. So that's a major difference if you work with Vector compared to mere security companies. And the experiences are quite wide. We work worldwide in all the destinations in US, in Europe, in Asia, with the tier one and OEM. And I invite you also to our annual Vector Forum, which is the 30th of June. It's online, it's global, and certainly you will benefit more than only security, because our topic this year is very interesting. It's about how to become a software company. And we have presentations from CARIAD, that's the software branch of Volkswagen. We have presentations from AST, which is in the semiconductor, Bosch, which you know from tier one supplier and also supplying whole systems. We have Eaton, which is a leading IoT supplier. And we have Marelli, the CTO of Marelli, Joachim Fetzer, will present also about recent evolution, which they have in this kind of companies, which are currently fast evolving into software business. And that being said, I thank you very much for listening to this webinar and would hope that you get a benefit from it for your own security testing. I look forward to hearing from you and wish you good success with cybersecurity. And of course, within this, let's say 45-minute webinar, we don't have the time to really dive into all specific testing techniques, but I hope that I illustrated the need for different methods, that I illustrate also that there are lots of methods behind, which you would not expect in an ISO standard, but which is really based on decade-long experiences in software verification and validation. We need tools, it's also important, but also remember that the fool with a tool is a fool. That is, first, the need is to have a method. Then you go with the respective tool. And there are lots of tools around. And I didn't even really look into our benchmarks on tools. We have published a benchmark on test tools recently in ATZ, and towards the year end, we publish a rather big article on testing tools in IEEE Software, which is the journal for the leading software practitioner. So have a look into these publications. We are extremely active in software testing, in cybersecurity, and of course many other topics, but this is what we talk here about. And stay tuned, www.vector.com/consulting. Appreciate your interest, wish you good success. And as I said, stay tuned. Thank you.